vrai que je te dis pas quand vous moquez de moi comme ça. Okay. Bon, bonjour à tous. Aujourd'hui, on accueille Laura Cobus qui a fait sa thèse à Winnipeg. C'est au Canada, voilà, au milieu du Canada. Et dans l'équipe de John Page. Et ensuite, elle est arrivée à l'Institut Langevin, une bourse Marie Curie, pour travailler avec Alexandre Aubry sur de l'imagerie. Donc là, c'est plutôt ses travaux de thèse qu'elle va présenter. Donc d'acoustique et de localisation, phénomène de localisation. Voilà. Du coup, Laura, je te laisse la parole.
Ok, merci. J'espère que ça gêne personne si je fais cette présentation en anglais. Non, ça va? Okay, good. Then I will switch to English. Yes, so as Juliette said, I'm going to talk today about some work that I did during my thesis a couple of years ago in the group of John Page. This was also a collaboration with another former student, Kurt Hildebrand, who was also in Winnipeg. And equally our theoretical collaborators, Sergei Skipichov and Bart van Tiegelen in Grenoble. And to a lesser extent, Alexandre Aubry at the Institut Langevin in Paris. Okay, so this will be quite an experimental talk. My goal is to illustrate some concepts using experimental measurements that I performed during my thesis. So I thought I'd start by introducing the talk by talking about this image here. So these pictures are experimental measurements that I made a few years ago. They essentially show acoustic waves in a sample of packed aluminum balls. So the samples look like this. They're essentially little aluminum beads that have been joined together by small necks. So these are solid cubes, which retain, however, the individual bead structure. So the diagrams here are essentially acoustic waves inside the samples measured at the face of one of these cubes. Okay, so they're measured. Essentially, we come in with a little probe here, send acoustic waves in. They essentially kind of fill the sample, and then here we have a laser interferometer, which we use to scan the surface of the cube. So these diagrams are different because they're measured for different frequencies of the waves. So they range from low frequency to higher frequencies. So at low frequencies, this means large wavelength. So here we can almost kind of see the extent of the wavelength over the face of the cube, which is bigger than the individual bead size. Whereas at high frequencies, or small wavelengths, what we get out is kind of more constant over the surface of the cube. So I'm showing this because we in this talk are going to be interested in frequencies in this sort of intermediate regime. And so specifically this means that the wavelength of the waves is about the size of the individual scatters. So it's about the size of the little metal beads. Okay. So we're interested in this regime because when you have wavelength about the order of the scatter size, you get multiple scattering of waves. So the waves are interacting with more than one scatter inside the sample. Now, to be clear, they don't exactly jump from scatter to scatter as I've drawn here, but this is a super useful picture to describe this kind of wave propagation. In fact, wave behavior can be described surprisingly well by a model of a random walk in which a little walker comes, hits the first bead, and then he takes a random direction until the next bead. Then he takes a random direction until the next bead, etc., etc. Can you kind of see this? It's a little GIF of a random walker. So this is the same model that has been used to describe, for example, the random Brownian motion of particles. So we can't predict exactly where the walker will end up, but we can estimate statistical quantities such as how far on average he can spread out. So to do this, we use a transport equation such as the diffusion equation. So it's basically, this one says that the mean squared displacement is proportional to time. So increases with time on a rate that's governed by the diffusion coefficient, d. So this is the same type of diffusion equation that is used, for example, heat transport in a solid. So the diffusion equation works really well to describe transport in multiply scattering systems for almost all situations. For instance, it tells us the intensity will spread out on average in space and time with a Gaussian profile as such. So cases in which diffusion doesn't properly describe multiple scattering can be called anomalous propagation. So we can create these situations in a couple of different ways. For instance, if we have a different step distribution than was assumed here, so the mean squared displacement has a different relationship to time, or we can have correlations between the steps of the random walker, which in this model we assume are completely uncorrelated, or we can have interactions between multiple random walkers inside the medium. So in this talk, this is the case that we're going to look at. And since we're looking at waves, interactions between random walkers means interference between different waves taking different paths inside the sample. So in this talk, we're going to look at some special cases where interference effects create anomalous behavior, so behavior that can't be described by diffusion. And these effects become especially important when we have strong scattering. So this means the waves scatter a lot inside the sample. They spend a great deal of time inside the sample. And so any interference effects that are there are going to become especially important. So I'm going to start by talking about the samples that we created to look at multiple scattering of ultrasound. Then we'll see some transmission experiments that we do to see if we can find such anomalous transport. Then we'll look at some reflection experiments in which we can directly see some of these interference effects. And then finally, we'll look at the most extreme example of such interference effects, which is called Anderson localization. OK, so here are the samples that we make. They're these sintered aluminum bead samples like we saw before with the cubes. But here we're going to make big slabs of them. So we start with individual beads, and we coat them in a material that lets them sinter together at high temperatures. So we put them in a big metal mold, such as we see here. And so we want the beads to be as disordered as possible so that they can correspond to the random walker model. So that's why this mold has essentially a bunch of dents that are randomly placed and with random depths so that the beads don't sort of self-order into a crystal. OK, so we pour the beads into the mold. Then we put them into this oven, and we heat the oven to a specific temperature so that beads which are touching sort of flow together, and then they solidify with these like solid necks between them. So we have this solid slab which retains the individual bead structure. OK, so all the experiments that we do on these samples basically involve sending in a short acoustic pulse and then looking at what comes out. So in transmission, what comes out is this field which extends super long in time. So all of these signals that are arriving at long times are waves that have been multiple scattered in the medium, so they spent a lot of time in the sample before escaping out the other side. Now, this transmitted field would be different if we make the measurement at a different spot inside the sample. And this is because it depends very much on the specific paths that the waves are taking inside the sample. So to be able to compare with theory, in which, as I said, transport is described by average quantities, we want to average over disorder to be able to compare with theory. So this is called a configurational average. Essentially, we want to average what we measure over different configurations of disorder. So for these large slab samples, that means that we can make measurements over different areas of the sample and then average these together. So to do this, we want to be able to move things around a little bit. The experimental setup is performed in large water tanks, partly because sound experiences almost no loss in water, and it couples very nicely between the water, the ultrasonic emitters and detectors, and the metal sample. So I have these big tanks. To be able to move things around inside them, we mount motorized stages on top, and then from these we just suspend a sample or transducers. So we can move them in all three directions if we like. Then we also suspend, of course, an emitter and receptor on either side of the sample to make transmission measurements. So here are some pictures of the actual setup. In emission, we want to input a pulse only at one specific spot at the sample surface. So we use a focused ultrasonic transducer. You can kind of see it here. So this sends a focused beam. And then to help the focused beam really only come in at one place, we use this sort of cone-shaped guide to really only make sure that we're inputting at this one spot. Then in detection, we have a small quasi-point-like detector that detects what comes out at really close to the sample surface. Now we want to be really sure that we only detect what's coming through the sample, and so we essentially divide the water tank in two with a large sort of plastic baffle. That's this white thing that you see here, so that really we don't have sound coming around the sides of the sample, but it's only going from emitter to detector. And we vacuum out the air, which is between the pores of the metal beads, so that we have sound only coming through the aluminum network and not through the air in between the beads. Okay, so then we can move the sample around to average over many configurations of disorder. The first thing we can measure is average intensity. So here we see for one frequency, we have our average intensity as a function of time, and which decreases as is predicted by diffusion theory. So we can fit the theory to the experiment. It fits very nicely. We need to know most of these parameters ahead of time. But then for other frequencies, such as this one, diffusion theory does not fit the experiment. So this could be due to anomalous transport, which cannot be described by diffusion. But we need to be a little bit careful because there was lots of parameters involved in this fitting. We might have estimated absorption wrong, etc. So for this reason, we perform a little bit more advanced transmission experiments to have more unambiguous measurements of anomalous energy transport. So what we want to do is look at the temporal and spatial spreading of the waves. So for this, we move the detector around in front of the surface of the sample. So we're actually measuring a whole map of the transmitted intensity, which has been input at one point on the other side of the sample. So diffusion theory tells us that the spreading of these waves should be Gaussian, as we saw earlier. So something like this equation. So here I've added absorption, which adds an extra exponential decay. And we can characterize the spreading using the width of the Gaussian, which depends on time, as we saw. So it increases, the width squared increases linearly with time at a rate which is governed by the diffusion coefficient, like we saw before. Oops, go ahead. Okay, so what's especially important is that we can take the ratio of these intensities, so the ratio of off-axis to on-axis intensities, and in doing so we cancel out most of the effects of boundary conditions, sample thickness, and absorption, which is super important, and we get a profile which really only depends on the transverse width, this width here, of the spreading intensity. So this lets us measure the width quite directly. So this is a direct measurement of the spreading in the transverse direction, so the spreading throughout the sample like this. So here we see the width squared, normalized by the sample thickness, as a function of time. So as predicted by diffusion, it increases linearly, and we can even use this to measure the diffusion coefficient just by fitting it with a linear fit. However, at other frequencies, the data does not fit the diffusion approximation. So we see even the way that the waves are spreading slower than has been predicted by the diffusion equation. So this is a more unambiguous measurement of anomalous transport. And now we would like to know what is its origin. So I actually already told you what the cause is. It's interference effects between different waves inside the sample. And we can use these, you can use reflection measurements to look more directly at some of these interference effects, which as we will see in the next part. So in reflection, the setup is pretty much the same, except we have detector and emitter on the same side, of course. And so to do this, we use an ultrasonic transducer array. So this is a collection of tiny transducer elements, which can each emit and receive independently from each other. So using this, we can first measure the angle-dependent backscattering. So we're going to measure the average backscattered intensity as a function of angle between source and receiver. Okay? So diffusion theory tells us that we should see nothing really special, just kind of a flat background, because the phase of the waves is randomized by the random position of the scatterers. So if we average over many different configurations of disorder, we're just averaging something random, and we should get a result which really shouldn't depend on the angle between source and receiver. However, if we actually do this measurement, we get something different. We get a sort of cone shape that's centered around 0 angle. And this is not predicted by the diffusion approximation. So this is due to an interference effect called coherent backscattering. This occurs when you have waves that take reciprocal paths inside the sample. So essentially, these two waves are taking the same path, but in opposite directions. And so what happens is that they interfere constructively when you measure them outside of the sample. And you get the highest constructive interference when the angle between source and receiver is 0. So you end up with this, on average, kind of this cone shape of intensity as a function of angle. Okay, so although coherent backscattering is not included in the diffusion approximation, it can be approximated as a sort of correction to diffusion. Because essentially, we've just not accounted for these reciprocal paths. And so I'm not going to show the calculation for the theory, but it essentially just involves manually summing up the contributions between all possible pairs of reciprocal paths. So when we do this, it gives us a correction to the diffusion equation. And this lets us fit our experimental measurements quite nicely. So here we see the coherent so the normalized intensity as a function of angle between source and receiver for different times. So you can see that the cone narrows as a function of time. And the theory now tells us that this narrowing, 1 over the width of the cone actually, squared, is proportional again to time times the diffusion coefficient. So in analogy to what we saw in transmission. So just like in transmission, we can plot this quantity as a function of time. So we get a nice linear curve. And we can use this again to measure the diffusion coefficient if we want. However, at different frequencies, we see measurements which do not agree with our theoretical prediction. So even though we've calculated a correction to diffusion to account for these different reciprocal paths, we still can't describe the behavior at all frequencies. So this means that the explanation for this is that we haven't taken into account enough of the reciprocal paths. What we've done is made a correction for the reciprocal paths, which have their beginning and end at the site of the sample that we're measuring. But in fact, they can occur inside the sample as well. And so, well, if we want to completely describe the propagation in this regime, we need to account for all the interference effects due to all these kind of reciprocal paths inside the sample. So to do this, the basic idea is the following. So we have these interference effects, and they are associated with an increase in the so-called return probability. So this is just the probability of your random walker to return to somewhere that he's previously been. So this is sort of sketched here with these little loops inside the sample. So if you have an increased return probability, then you're going to spend longer inside the sample because you're going to keep coming back to somewhere you've previously been. And so this is going to decrease diffusion because it'll take longer to spread out and longer to get outside of the sample. Okay? So you have a decreasing diffusion. So this means that your diffusion coefficient should be renormalized. It should be smaller, right? Because diffusion is now slower. And so you have this process which is actually successively happening. So the longer you spend inside the sample, the more the diffusion is renormalized and it gets smaller and smaller. So if we want, we can describe this mathematically using a diffusion equation to which the solution is a return probability. And then we can also have another equation which links an increase in return probability to a decrease in the diffusion coefficient. And then one solves these two equations self-consistently to find the diffusion coefficient as a function of time. So, and so what is nice, so this seems like a reasonable description, very intuitive. And what's really nice is that we have been able to measure somewhat directly the return probability and observe this behavior. So the experiments are performed in the same way as with the previous ones in the reflection geometry. But this time we're measuring only the signals that are going, that are input and output at the same spot on the sample surface. So we're kind of directly measuring the signals that are input, and they make some kind of multiple scattering path inside the sample, and they come out at the same spot. And so this is rather direct measurement of the return probability. The waves are returning to somewhere they've previously been. So we can plot this as a function of time. It decays as a function of time. In the diffuse regime, we already have predictions that tell us what should happen, and they fit quite nicely to the experimental measurements. Then we see that at these same special frequencies where we have anomalous behavior, the return probability increases. So we're observing what we had previously sort of intuitively predicted. The return probability is increasing, the waves are coming back to the same spots again and again, and diffusion is becoming renormalized. So the most extreme sort of end of this is an effect called Anderson localization. So I'll go back to this slide. We have diffusion, which is becoming renormalized. So the diffusion coefficient is becoming smaller and smaller. This is actually called the self-consistent theory of localization, because if you follow it to its logical end, the diffusion coefficient becomes smaller and smaller until eventually it should go right to 0. In which case, you don't have diffusion, so the waves become confined in the sample on a scale which is called the localization length. So Anderson localization is really the most extreme example of renormalized diffusion. So if we go back to our data with the mysterious deviations from before, this is our measurements from transmission and reflection. We can fit them with predictions from this theory, the self-consistent theory of localization, or the theory of renormalized diffusion. And we see that they fit very nicely to all of our experimental measurements for these different frequencies, which could not be described by diffusion. And in fact, by comparing our data with this theory, the data tells us that at certain frequencies, we are actually in a localized regime, so the waves are trapped inside the sample. So Anderson localization is not just a phenomenon for acoustic waves. It's actually important for a very oops, I'm cut off there a little bit. That says Anderson localization. It's actually important for a very broad range of fields. It was originally proposed in 1958 in the context of charge diffusion and quantum spin diffusion. So the idea here is that you have a lattice of potential wells on which an electron can tunnel from site to site. And the potential wells have a random distribution of energies, this potential energy VR. So if the electron has enough energy, he can hop wherever he wants, like in a metal. But below a certain energy, he becomes trapped, not just in one potential well, but just because of the disorder of the energies of the wells. So of course, in between, there's some kind of transition. So for a critical energy, there's actually a phase transition between diffusion and localization. And this happens only for 3D systems. So, and then you get the localization length, which is the spatial extent of the wave functions, diverging actually at the phase transition. So then the theory was later extended to classical waves. So the main difference here is that we have a slightly different wave equation. So here the disorder comes in, not in energies of the lattice sites, but in the disordered scattering cross-section. So for instance, if you have our sample of beads, the disorder is in the positions of the different scatterers. So again, in 3D, you have a phase transition between conventional diffusion and the localization regime, which is governed, for instance, by changing frequency. So that's what you were doing before. We changed the frequency, and then we went into a different regime. So far, the only observations for Anderson localization for classical waves in 3D were made in the group of John Page, my old PhD group in Winnipeg. So we've shown that by comparing our data with the theory, the renormalized diffusion theory, we can describe the behavior very well. And in fact, this lets us measure the localization length, so the spatial extent of the waves, as a function of frequency. Okay, so we saw that at low frequencies, we have conventional behavior, which can be described by the diffusion approximation. But then as we increase frequency, we go into an actual phase transition into a localized regime where the waves find it much harder to escape the sample. we actually found 2 phase transitions. So this means that we saw an entire localization regime bounded by a diffusive regime on either side. Oop. Okay, so just to sum up, we've seen that in almost every situation, the multiple scattering of waves can be described nicely by the diffusion equation, which is based on a random Walker model. And we can usually ignore the fact that waves have phase because we can describe the propagation using average quantities. But if interference becomes important, we need to take it into account, which one can do using a renormalized diffusion model. The most extreme end of the renormalized diffusion model is Anderson localization, so the absence of diffusion. And we can also observe rather directly these interference processes that are responsible for localization, such as the return probability. And that's it. Thank you.
Quelqu'un a des questions?
So, did you try to fit your data for the Anderson localization to find a critical exponent? And does that work with the theory?
We did try, but it did not work yet. It's very hard because, well, one of the reasons that it's very hard is because at this critical regime, you just have a crazy amount of fluctuations. And so you need a lot of configurational average, like a lot. And so we didn't have enough.
Thank you so much. I'm just curious, because in your work you have been basically targeting from the beginning like the classical random walker, which obviously in the large experimental setup, the big perspective is that it returns to the normal distribution, which is actually why we have the connection, the wonderful connection to the diffusion. But for example, in this case, seeing like the weirdness that we get in different frequencies, did you like try any of the quantum distribution? Like for example, considering instead of the classical random walker, like a quantum random walker, and maybe explore the connections with Fermi-Dirac or Bose-Einstein distributions, because these are similar. They are like the quantum counterparts of the classical perspective that we have over here. Just as a comment, probably.
Oh, no, it's a great question. I am an experimentalist, so I have not done this, but there has been a lot of work, theoretical work on Anderson localization, so I'm imagining that somebody has explored these areas.
I will be very curious because actually, like the middle graph, I can immediately recognize it as a Bose-Einstein condensation that you actually managed to capture over there.
The one of the phase transitions?
Yes.
Yeah.
That's why I was actually kind of triggered, or at least curious about this. Maybe there must be a connection. Maybe I don't know. Maybe later on. Thank you.
I'll think about it.
I have a naive question.
Yeah.
It's can you figure out a medium that will enhance the localization? So you take a frequency and you decide where to put the structures in your medium.
Yeah, for sure. I mean, already these samples were designed to enhance localization. It's complicated because there's some factors that we don't still quite understand about how it occurs. But one of the important things is to have, we think that localization can be associated with a lower density of states. Oh, actually, I maybe have an extra slide for that. So, if we look at the average transmission as a function of frequency for these samples, then we actually see regions of high transmission and then also band gaps. So actually, interesting question. Why would we have band gaps if the samples are completely random? No? Yeah. So it's because of the way sound propagates through the samples. It doesn't propagate as if through a solid, but it's really coupled resonances of the individual beads. So actually here we're plotting resonances of the individual aluminum beads. And so if you have an area where you start to have a lot of resonances, then they sort of couple together and you have transmission. But other areas, you just don't have transmission there. And so actually we've seen that localization tends to occur more in these band gaps, or transmission gaps is better to call them. And so these can be enhanced by having less coupling between the beads, so that you have this more extreme effect. Does that make sense? So one way to do that would be to have smaller, like, necks joining the beads.
Okay.
Does that make sense?
Yeah, it's an answer.
So for the Anderson localization, were you expecting to have a band of frequency or only one frequency for the transition?
It had never been observed before, but it is logical because at way higher frequencies you also see diffusion again. And so the initial experiments had not observed the second phase transition because since they were performed in this band gap, there just wasn't enough signal. But it makes sense because localization occurs when you have very strong scattering. And for classical waves, this occurs only in this intermediate frequency regime, which we saw way at the beginning. So it means that you have, at lower frequencies, you have diffusion. And then at higher frequencies, you also have diffusion. So, I mean, it makes sense to have two transmissions into localization.
The question about working in audio, for me, 1 megahertz is not low frequency. So it's funny to hear low frequency. But what is striking is the fact that you can go from what you call low frequency to high frequency just with a factor of 2. Well, if I think about our work in audio signals, then low frequency would be a few hundred hertz, and then high frequency is more like a few thousand, so more like factors of 10 at least. Or so. Could you comment on this? Or?
Yeah, I mean, we actually do have access to this whole frequency range, which is almost a factor of 10. But the localization, like the regime that we're interested in, is really this intermediate frequency regime here-ish. And the Anderson localization regime is very narrow. It's like in here. I'm not totally sure why. I'm sure it's due to the nature of the resonances in the sample. This is a thing for future work, yeah. Because it'd be easier to study if it was way bigger, so. Other questions?
Could you tell us a bit more what you're doing now?
Now I'm doing something quite different. So I'm doing more of an applied project, also mostly using ultrasound, but this time for imaging. So we take a reflection matrix approach to imaging, where, let's go back. Come on. Ha. Right? Yes, okay. Where we use ultrasonic transducer arrays like this to acquire a reflection matrix. So this is essentially a matrix of responses between each emitter and receptor in the array. So you emit with the first one, and then you receive with all the other ones, and then you emit with the second one, and you receive with all the other ones. And so you have this matrix of responses between emitters and receptors, which holds a lot of information about the medium. And so the idea is to extract this information to perform imaging. So we are applying this mainly to medical ultrasound imaging, and then also have some applications in optics.
Bon, du coup, on va remercier Laura et du coup, si vous avez des questions plus tard, voilà. Et sinon, de toute façon, elle travaille à Institut Langevin, donc juste en face d'ici. Merci beaucoup.
Merci.